All right, so let's basically kind of summarize the patterns and behaviors that we saw from a decay function. And pretty much a lot of the same information that we mentioned for the growth function. Number one is that it is still going through the point 0, 1. So it has a y-intercept at 0, 1. And then what we saw if we start going in the negative x direction, the function's actually on its way up. And if we go in the positive x direction, the function starts to basically get closer and closer to the x-axis. And so again, in terms of an x-intercept, since we're never crossing it, there is none, right? There is no x-intercept. The domain, like the growth function, is also all values. The range is from 0 to infinity because the graph is always above the x-axis, it's never below. All right, and so we can kind of see all that behavior going on. And then we still have a horizontal asymptote. Now, of course, the horizontal asymptote behavior is a little bit different, right? Because it's still the x-axis, or where y is equal to 0, but it's happening when x gets bigger, right? When we're going to positive infinity. For the growth model, right, that behavior was over on this side, but now the asymptotic behavior is over on that side. All right, so there's much more we could say about this, but as you guys get to know more details about functions, I'll let your 151 instructor add that. But for what we've learned, right, we've learned about intercepts, and we've learned about domain and range. And then there is a new topic about horizontal asymptotes. So in this case, we do have a y-intercept at 0, 1. We have no x-intercepts. We have a function that's very strong. It's defined for all values of x. And then as far as the range is, it's limited by being positive all the time from 0 to infinity. All right, and as far as famous, oops, I made a mistake there. As far as famous decay functions are concerned, well, again, it deals with that crazy number, e, but this time we're raising it to the negative x power. And oftentimes you might even see base 10 to the negative x power. But this guy is the big one. Again, in many circumstances, as we solve equations, we end up getting e. And one of the most famous situations is that of a radioactive isotope. All right, you guys have probably heard of radioactive decay. What ends up happening in a radioactive decay situation is we'll start off with so much of a substance, let's say like 50 grams, and then over time what happens is the substance actually decays relatively fast, but slowly but surely it stops its decay. It's going to 0. It eventually will go away, but very, very slowly. It's always going to leave some sort of a trace amount. And then maybe something that hits a little bit closer to home is how temperature behaves, right? If let's just say I have a cup of coffee, right, and it's heated to, let's say, 150 degrees, that's pretty hot, right, and I put it on a table where it's just going to be sitting in room temperature, then what I expect, right, is as time goes forward, it's going to start at 150, but it's actually going to go down, right? Let's say it's outside, we're in Minnesota and it's 0 degrees, right? So it's going to basically go down like so. It'll eventually cool off to the surrounding temperature, and that's actually what does happen. Whatever that surrounding temperature is, it might start off at 150, but if we're sitting in a room that's at 70 degrees, it's going to go down really quick and then just taper off towards that 70 degrees. So it behaves like an asymptote. But we're not going to see that in this class. Most of ours are going to behave exactly like we expected to have, is that the x-axis will serve as that asymptote. But hopefully that just gives you an idea of some famous decay functions and some of the applications that you might see them in future classwork that you do. All right, so there's your quick summary of the exponential decay function. We'll wrap this up by doing some relatively simple applications, but I'll do that in some new videos coming soon. Talk to you later.